Question 17. Which alcohol can be oxidized by acidified potassium dichromate? So that's orange and it will go to green, and it will oxidize primary and secondary alcohols. It won't oxidize tertiary alcohols, but cannot be dehydrated by heating with concentrated sulfuric acid. So let's first of all get rid of any tertiary alcohols because they won't be oxidized by potassium dichromate. A tertiary alcohol is where the C with the OH has 3 other carbons bonded to it. So the C with the OH has 3 other carbons bonded to it. Let's have a look at this. Butan-2-ol. So the OH is at carbon number 2. So it's in the middle of a chain at carbon number 2. It's got carbon number 1 and carbon number 3 around it. Is there a methyl group at carbon number 2? Yes, there is. There's 2 methyl groups, one at carbon number 2 and carbon number 3. So on carbon number 2, it's got a carbon on carbon number 1 and a carbon alongside it to the right on carbon number 3, and it's got a methyl group at number 2. That OH is surrounded by 3 carbons. That's a tertiary alcohol. It's not going to be oxidized by acidified potassium dichromate, so we can rule out A. Let's have a look at C. 2-methyl-propan-2-ol. 3 carbons in a line. The OH is in the middle of the 3 carbons at carbon number 2. So it's got carbon number 1 and carbon number 3 either side of it. Oh, and at carbon number 2 it's got a methyl group as well. So that carbon number 2 has got the OH, it's got a methyl group, and it's got a carbon either side of it, 1 and 3. So the C with the OH at carbon number 2 has got 3 other carbons around it. That's a tertiary alcohol as well. So A and 3 are not going to react with acidified potassium dichromate. Propan-1-ol, so you've got at carbon number 1, you've got the OH, and you've got methyls at carbon number 2. That looks as if that's a primary alcohol. Pentan-3-ol, 5 carbons, and the OH is in the middle at carbon number 3, but it would have 2 carbons either side at carbon number 2 and 4, and an H off carbon number 3. That would be a secondary alcohol. So B and C could be oxidized by acidified potassium dichromate, the primary alcohol and the secondary alcohol. The question is, which one wouldn't be dehydrated with concentrated sulfuric acid? So what you need for the concentrated sulfuric acid, what it does is it takes the concentrated sulfuric acid, removes water. It removes water and dehydrates something, removes water by removing an OH from one carbon and removing an H from the neighbouring carbon. So you need an H on a carbon, and on the neighbouring carbon you need an OH. So presumably one of them hasn't got an H on the neighbouring carbon. Let's have a look. Propan-1-ol, so the OH is on carbon number 1, and on carbon number 2, you've got 2 methyl groups, and you'll have a carbon number 3 as well joined to it. So that carbon number 2 has got 2 methyl groups, and it's got carbon number 3 joined to it as well. So that carbon number 2 there hasn't got an H joined to it. So it's not got an H on carbon number 2 that can be removed along with the OH on carbon number 1. B cannot be dehydrated with concentrated sulfuric acid. So that must be your answer, answer B. Let's just check out D. D has got an OH at carbon number 3, and at carbon number 2 or at carbon number 4 it must have an H. So that will have an H at carbon number 2 and no H at carbon number 3. We'll also have an OH at carbon number 4 and no H at carbon number 3. Yes, it's got an H and no H on neighbouring carbons. That would be dehydrated. Your answer is B. How many structural isomers are there with the molecular formula C3H4BrCl? So I'm just going to do spoilers on this so we can see it a little bit better. C3H6BrCl. So you've got 3 carbons in a line, you've got 6 H's, and you've got a Br and a Cl. So the question is, where can the Br and the Cl's go? What combinations can we have? So at carbon number 1 we can have a C, and we can have the Br also at carbon number 1. So both the Br and the Cl at carbon number 1, and the H's then are just on the other carbons. We could have a Cl at carbon number 1, a Br at number 2. We could have a Cl at carbon number 1, a Br at carbon number 3. I think that's all the combinations with a Cl at carbon number 1. With a Br at carbon number 1, also carbon number 2 or carbon number 3. Therefore, the next combination is a Cl at carbon number 2. Well, you could have a Br also on the same carbon, or you could have a Br at carbon number 1. Remember, if the Cl is at carbon number 2, then carbon number 1 and 3 either side are effectively the same, depending on which end you label them at. So say for example, if you have a Cl at carbon number 2, then the Br at carbon number 1 is the same as at carbon number 3. And similarly, if you have a Cl at carbon number 3, that's the same as at carbon number 1. So your answer is B, 5 different combinations.